One frequently asked question we've been getting is about polarity. This is generally being asked about a specific set or a specific video in the general chemistry section. I'm going to try and clear up what exactly makes a certain molecule polar or nonpolar. So in order to be polar, a molecule needs two things. It needs to have polar bonds, or in other words, it needs to have differences in electronegativity between its atoms. And we'll get into some examples later where I'll show you exactly what that means. The second thing a molecule needs in order to be polar is it needs to have an asymmetrical molecular geometry, meaning that its dipoles cannot cancel each other out. And again, I'll show you in these examples exactly what that means. Let's start with kind of a fictional example. We have a carbon that's bound to 4 other carbons. That's not the fictional part. The fictional part is that these outside carbons aren't bound to anything themselves. So that's the fictional part. But pretending this molecule could exist as is, let's ask ourselves, is this molecule polar? Does it meet criteria 1? Does it have polar bonds? Or in other words, are there differences in electronegativity between its atoms? The answer is no. This molecule does not have polar bonds because the central atom, the carbon, and the atoms it's bound to, also carbons, have the same electronegativity. So there's no polarity. None of these carbons out here are pulling on the electrons in the bond any more than the central carbon is. So the bonds are not polar. It does not have asymmetrical molecular geometry. In other words, it does have symmetrical geometry. You'll learn more about that in future organic chemistry videos, but this is in the shape of a tetrahedron, which is symmetrical. Okay, these next 4 examples are molecules that we get questions on a lot. One of them is BF3. If you draw out the Lewis dot structure of BF3, it looks like this, where the boron has no lone pairs on it. Each of these fluorines would have 3 lone pairs around it. I'm not going to draw them just for simplicity's sake, but that's how it looks. So we ask ourselves, is BF3 polar? Well, does it have polar bonds, or are there differences in electronegativity between its atoms? Yes, there are. It has very polar bonds. Fluorine is the most electronegative atom, or the most electronegative element there is. So these fluorines are all going to be pulling electron density towards themselves and away from the boron. So yeah, it does have polar bonds. We next ask ourselves, is BF3 asymmetrical? No, it has symmetrical geometry. See that each of these fluorines is the same distance apart from one another. So they form this symmetrical equilateral triangle around the boron. So BF3 does not meet the second criteria of polarity, which is asymmetrical molecular geometry. But how can we make this easier to see? Students seem to have a difficult time seeing this or understanding exactly what we mean when we say asymmetrical geometry. Well, the way I always imagined it was using the image of tug of war. So if each of these fluorines is a team of tug of war players, or a tug of war player on their own, and they're trying to pull the central atom towards themselves, and these bonds are like their ropes, which of these atoms is going to win? Well, and we can compare their strengths, the strengths of these tug of war players, to the bond polarity. Because we have 3 of the same atoms, they're all fluorines, they're all going to have the same polarity, or in other words, they're going to have the same strength in our game of tug of war. And notice that they're each pulling in directions in such a way that the boron will not move. We can see this a little more technically by drawing out the vectors that they're pulling the boron with. So let's draw this first vector right here as a dipole. We're going to say that this fluorine is pulling in this direction with a certain amount of strength. This fluorine is pulling in this direction with a certain amount of strength. So we draw this vector. In order to see the sum total of these forces on the central atom, we draw these vectors end to end. So now we're going to draw the vector that this fluorine creates. It's pulling in this direction. It has equal strength as the first arrow we drew, so they're going to be the same length. That's how we're representing strength here. So we drew them end to end because we're trying to find the sum total of these vectors. Now lastly, we're going to draw the vector from this third fluorine. It's pulling directly up on the boron with the same force as these other 2. So in order to find the sum total of forces, we look at where we started drawing our first vector and where we ended drawing our last vector. And if there's a difference between them, then there is some difference in the dipoles of the molecule. In other words, the molecule is polar. But here you can see we started and ended at the same point. Our vectors all cancel out perfectly, meaning that there is no polarity in the BF3 molecule. So again, you won't be asked to draw vectors on the DAT, but it can help you visualize what I'm talking about. If the tug of war thing doesn't make sense, then hopefully this will make sense. But again, if you're more comfortable with the tug of war, I just always imagine these as being like trucks or tug of war teams that are trying to pull the boron towards themselves. If you had 3 trucks of equal strength hooked up to ropes trying to pull on a molecule and they're each driving 120 degrees apart from each other in a perfect triangle, that central object is not going to move. The next common example we get asked about is CCl4. Carbon was going to be our central atom here. Each of the chlorines will have 3 lone pairs around them, and carbon's not going to have any lone pairs around itself. It's happy having these 4 bonds exactly like that. So we ask ourselves, is this molecule polar? Well, we do have polar bonds. The chlorines are more electronegative than the central carbon. So the bonds are polar, but that doesn't mean the molecule itself is polar. We just have polar bonds. The next question we ask is the molecule asymmetrical? Well, if you remember from this molecule up here, tetrahedrons are symmetrical. So we can say that this molecule down here is symmetrical. It does not have asymmetry and therefore will not be polar. Let's look at it using the same tug of war or vector analogy we used in the previous problem. You can see that these 2 chlorines are pulling exactly opposite of one another. And these 2 chlorines are also pulling exactly opposite of one another. So they cancel each other out. Now, if you know a little bit more about stereochemistry, that analogy kind of breaks down. Let's draw out the vectors themselves. Let's draw them in this order. So we're going to draw this vector first. This vector looks like that, this dipole. Then we're going to draw this. Then we'll draw this vector. It's pulling on the carbon up and to the left. So that's why I draw it going up and to the left from the end of the previous vector. And then lastly, we're going to draw this vector. See, we started and ended at the same point again. And what that tells us is that the polarity of these bonds perfectly cancels one another out so that this molecule is not polar. Hopefully that makes sense. Now the last molecule we get asked about again because it's in some of our quiz questions, and I think it's in one of Mike's videos, is SF4. So you may be tempted to draw the structure of SF4 like this. However, if you did that, you'd be incorrect. Remember that sulfur, like oxygen, wants to own 6 electrons. Here it only owns 4. It owns 1 of each of these bonds. It's also important to remember that sulfur can break the octet rule, as it does here. So the actual Lewis dot structure of sulfur tetrafluoride looks like this. Let's go about determining if this molecule is polar or not. First, does it have polar bonds? Yes. Fluorine, as we already talked about, is the most polar element on the periodic table. It's going to be pulling electron density towards itself away from the sulfur. We do have polar bonds in this molecule. Is this molecule symmetrical? Well, if in your mind you're imagining that this molecule has the same shape as this molecule, or this molecule being tetrahedral because it has 4 bonds, you'd be incorrect. Sulfur tetrafluoride is not in a tetrahedron. Its molecular geometry actually looks like this. Some people call it a seesaw geometry, where this fluorine is actually kind of going into the page away from us, and this fluorine is coming out of the page and towards us. And the lone pair up here causes these groups to not be in a tetrahedron. It pushes them down into this seesaw-like shape. So we've established that this molecule has polar bonds. Now we're talking about, is this molecule symmetrical? You may say, yeah, it's symmetrical. It looks the same on both sides. But what we really mean when we're talking about symmetry is, do the dipoles of the polar bonds cancel one another out? Well, we can do the same thing we've done in previous problems. We can look at this as a tug of war and say, well, these fluorines are pulling exactly opposite of one another, so those will cancel out. These 2 fluorines down here, however, are not pulling exactly opposite of one another. They're pulling exactly opposite of one another in the right and left directions, but not in the up and down direction. There's no fluorine opposing the force that these 2 fluorines are pulling down on the sulfur with. There's nothing pulling up on this central atom. Let's draw the vectors out just so we can see this a little more clearly. We'll start with this vector. It pulls straight to the right. This vector pulls straight back to the left. Okay, we're back where we started. So from the end of what we just drew, I'm going to draw this fluorine's vector. And again, if you know a lot about stereochemistry already, you're going to see ways in which this could be a little more accurate, but we're going to neglect stereochemistry for the time being. So we're going to draw this fluorine's vector. It's coming kind of down and to the right. That needs to be a little longer to match up with the other one. It's coming down and to the right. Now we're going to draw this fluorine's vector. It's going down and to the left. This is the first molecule we've drawn that is in fact polar. And remember I said clear back in the beginning that in order to see if a molecule is polar, you can draw out its vectors like this, and then you draw a line from the from where you started drawing your vectors to where you ended up. Here we started drawing our vectors here. We went right and then back, and we ended down here. So let's draw a line down to where we ended up. I'm going to do that in a different color to make it a little more clear. We draw a line down to where we ended up. This is the resulting vector. This is the resulting dipole on SF4. And it makes sense that our dipole would be down from the sulfur atom because these two fluorines oppose each other, as we said, in the left and right direction. So their left to right direction cancel each other out. However, their downward pull on this sulfur is not countered by any upward force on the sulfur. So sulfur tetrafluoride has this net dipole down. And that's what we mean by symmetry and molecular geometry. That's what you need to look at. So again, hopefully this video was helpful. Hopefully it helps you see how a molecule like BF3 that has polar bonds but has a symmetrical molecular geometry is not polar, and a molecule like SF4 that has polar bonds and is asymmetrical is polar.